Following video is for Calculus AB Chapter 4 review. The following problems we're going to do without the use of a calculator, which means that you should be able to do the problems without a calculator. So the first problem says for y equals x to the fourth minus 72x squared minus 17, find the exact intervals on which the function is increasing, decreasing, concave up, concave down, and the local extreme values, if any, and point of inflection. So we're going to do the increasing, decreasing, and local extreme values because they're the same thing. So to find whether a function is increasing or decreasing, I have to find the first derivative. So my first derivative is going to be 4x to the third minus 144x, and the derivative of 17 is 0. Now that I have my derivative, I'm going to go ahead and set that equal to 0 and solve. So I'm going to find my critical points. So these are called the critical points. And critical point happens when the derivative is equal to 0 or the derivative does not exist. So as we factor 4, we're going to factor 4x, we get x squared minus 36 equals to 0. So if I use the zero product property, so I have x is equal to 0, so that's the critical point, and x squared is equal to 36, so x equals plus or minus 6. So those are also critical points. So I am going to do a number line on negative 6, 0, and 6. And since I'm checking whether I'm increasing or decreasing in local extreme values, I'm checking the sign of my first derivative. So I need to check the sign of the first derivative. And I'm going to substitute them into my first derivative. So I'm going to need a number to the left of negative 6. So let's do negative 7. So negative 7 squared is 49. So 49 is larger than 36. So this is going to be positive. And 4 times negative 7 is a negative. So a negative times a positive is a negative. So I need a number between negative 6 and 0. So negative 1. So negative 1 squared is smaller than negative 36, so that's a negative. And negative 1 times 4 is a negative, so a negative times a negative will give me a positive. So number between 0 and 6, so let's do 1. So once again, 1 squared is smaller than negative 36, so that's negative, and 4 times 1 is positive, and a positive times a negative is a negative. So a number to the right of 6, I'm going to use 7. So 7 squared is 49, which is bigger than 36, so that's a positive, and 4 times 7 is a positive. So a positive times a positive is a positive. So I end up with this. So I have that my function is increasing here, right, decreasing there, increasing, decreasing, increasing. So that means that, remember, once you're done checking the point, cross them off, because that's not part of your solution. So negative 6 is going to be a local min, 0 is a local max, and 6 is a local min. So the way I would write this is part A, it says where is it increasing? I am increasing from negative 6 to 0, from negative 6 to 0, and from 6 to infinity. And if they ask you why am I increasing? I'm increasing because the first derivative changes signs from am I decreasing? I am decreasing from negative infinity to negative 6 and from 0 to 6 because the derivative changes sign from negative to positive at this endpoint. And I'm going to go ahead and do E as well. So E says, find my local extreme value, if any. So I'm going to just do the x values of my local extreme values. Since I don't have a calculator, it's going to be really hard to calculate them. So the x value is going to occur when x equals negative 6 and x equals 6. Those are local min. And when x equals 0 is the local max. Okay, so now I can do when it's concave up or concave down. So I'm going to do C and D. To find where it's concave up or concave down, I need to take the second derivative. So this is C and D, and I'm also going to do F at the same time. So to find the second derivative, so I'm going to use before I factored it because it makes it easier. Otherwise, I'm going to have to use the product rule. So I'm going to have 12x squared minus 144. And I'm going to set that equal to 0 because I'm looking for possible points of inflections. So I'm going to have 12x squared equals to 144. So x squared is equal to 12. So x is equal to plus or minus the square root of 12. So this is possible points of inflection. So I'm going to check my points. So I have negative square root of 12 and positive square root of 12. So since I'm checking to see whether I'm concave up or concave down, I'm going to be checking so because I'm checking whether my function is concave up or concave down, I need to check the sign of the second derivative. So I'm going to be using the second derivative. So I need a number to the right of the square root of 12. So that would be about 4 because the square root of 16, right? I don't have a calculator, so I kind of have to think logically. Negative square root of 16 is bigger or smaller than negative square root of 12. So I'm going to check negative 4. So if I substitute negative 4 into here, I get 16. And 16 times 12, that's going to be bigger than 144. So that's going to give me a positive. So now I need to check a number between negative 4 and 12. So I'm going to check 0. So if I substitute 0, I get negative 144. So that's a negative. And a number to the right of the square root of 12. So once again, I'm going to use the square root of 16, which is 4. So 4 squared is 16. 16 times 12 is still larger than 144, so that is positive. So once you're done checking your numbers, cross them out because you don't need them. So what this tells me is that my function is concave up in this interval, down here, and up here. And these are my points of inflection. So in part C, where it says where is it concave up, I am concave up from negative infinity to negative the square root of 12, and from the square root of 12 to infinity. Why? Because the second apologize for that. It is because, why am I increasing? I am increasing because my first derivative is positive. I am decreasing because my first derivative is negative. The next problem says, let f be the function defined on the closed interval from negative 5 to 5. The graph of the derivative consists of two semicircles and two lines as shown below. So we are given the graph of the derivative. So this is important because remember, if we're looking at the derivatives, anything above the x-axis, that means f is increasing. Anything below the x-axis, that means f, my original function, is decreasing because we're looking at the graph of the derivative. So part A says from negative 5 to 5 on my interval for all values of x, find all values of x which f has a relative maximum, and justify my answer. So I know f has a relative maximum if my derivative is equal to 0. Okay. So that is the same thing as saying the x-intercepts, because when, right, f is another word for y, so when y prime is equal to 0, that's the x-intercept. This is f prime, which is y prime. So we're looking at my graph. So where are my x-intercepts? My x-intercept is right here, right there, here, and here. So where are my relative maximum? So notice that I'm going above the x-axis here. So my function is increasing here. Notice that from negative 3 to 1, it is below the x-axis. So my original function is decreasing in this interval. From negative 1 to 4, I'm above, so I'm increasing. And from negative 4 to 5, I'm below, so I'm decreasing. So as we do a number line, it kind of makes it a little bit easier to see. We have negative 5, negative 3, 1, and 4. These are all my critical points. Okay, those are critical points of f. So I'm positive here, I'm increasing. My derivative is negative there, so I'm decreasing. My derivative is positive here. The reason it's positive is because it's above the x-axis. So when my x value is 2, my derivative is positive 2. And then from 4 to 5, I am below the axis, so it's negative. So which ones are my relative maximum? My relative maximum is going to occur here, because I'm going from positive to negative, and right here at 4, because once again I'm going from positive to negative. So which ones are my relative maximum? When x is negative 3 and x is equal to 4. Part B says for negative 5 to 5, find all values of x which f has a point of inflection. So and it says justify your answer, and your justification would be the same thing, because the derivative changes sign from positive to negative at these points. So that would be my justification. So remember, this point of inflection occurs when the second derivative is equal to 0. So that means I am looking to see where the tangent line of the first derivative is horizontal. So that's where I'm looking at. notice that at negative 4, I have a horizontal tangent. I also have a horizontal tangent at negative 1. And at 2, this is where the second derivative does not exist because I have a corner. Remember, I'm looking at the first derivative. So if we do a number line, just to kind of give you an idea, and I'm checking the second derivatives, so I'm negative 4, negative 1, and 2. So these are possible points of inflection. So notice that my derivatives, my tangent lines are positive. So I'm positive to the left of 4. My tangent lines are negative to the right of 4. So notice I'm still going down, and then I'm going up again. So I'm at positive, and I'm still positive, and to the right of 2 I am at negative. So all of these are points of inflection. So the points of inflections occur at negative 4, negative 1, negative 2. And that is going to be because the second derivative changes signs at these points. Okay. Part C says find all the intervals in which the graph is concave up. Where it's concave up, where the second derivative is positive. So I already have it from part B. So where is my second derivative positive? It is positive from negative 5 to negative 4. Remember, it's not negative infinity because we start at negative 5. And from negative 1 to 2. Those are the intervals where it's concave up. Why?